Hello, welcome back to our discussions of Java. This time we're going to look at Java value types and reference types as another way to look at primitives and objects. And this will be important in understanding how method parameters work at a deeper level, which is our next topic. So the value type. Language primitives in Java are value types: int, bool, double. The value is stored directly, and the computer uses a number to refer to the memory location. The high-level language pastes a variable name onto the side of the box for the human being, which disappears when the program is compiled. So let's look at the example on the right, where we have memory location 2051, variable name also pasted on, right? So human being referred to that memory location as A, whereas the compiled software refers to it as memory location 2051. In either view of it, the value, int value, is stored inherently in that box. So that's why we've never done new int, new of any type of print. When that code below, int a, that declaration is also the allocation. So that 80 goes directly into that memory location. It's a direct thing. It's a value type, a direct thing. Now, b is also, and I'm not showing this, but int b declaration. This is a deep copy. So B also has its memory location, being a primitive, and it's set to the initial value of A. From then on, they have different lifetimes. A is changed, B is not affected. B is changed, A is not affected. The reason for that should be clear. They both have different memory locations. B is just simply initialized to the value of A. So B is always a deep copy of A. So primitives are always deep copies of one another if you set them to one another. Right? Reference types. Objects are reference types. So that's why we began this discussion with the title Java Value and Reference Types as another way to look at primitives and objects. Primitives are value types in Java, and objects are reference types in Java. So look at our picture. A and B contain the address of an object. Here's an analogy. The address of a house on an envelope. The address is the reference, and the house is the object. Analogies can be oversimplifying but useful, but in this case, the analogy is really not oversimplifying. A, employee A here, look at the code here on the right. Employee A, that's enough memory location there to hold an address. So all reference types are really the same size. They hold enough to hold an address. The same way, let's say the address of an envelope that goes to the Empire State Building is the same size as the address on an envelope that comes to my house, which is nowhere near the size of the Empire State Building. It's enough memory to hold the address that then has to get dereferenced to get to the actual memory location. So the process of that, the reference type stores a memory of the value, and to reach the value, the memory location is dereferenced. It's looked up. Okay. So this is where we get the concept of a shallow copy. A equals new employee. That new employee, the new operator, goes to the heap and allocates the space for employee. Let's back that up a little bit and see what the class has done. In the past, we've said what the compiler has done. The compiler has seen class employee declared, and it notes down how that layout is. The class is the template for the object. So that new employee, the compiler has been about the class employee. It's a template. It goes out to the heap and lays onto the heap that template. And let's say you have maybe 100 different attributes of employee. The compiler has calculated the necessary space to hold those 100 attributes and all the methods of that employee as well. And it stamps out of memory enough space to hold that object. So A is now referring to a legitimate memory location. So when age is just a slice of that. So again, the compiler is doing the math. A holds the reference address, and age is some offset from that beginning address to set that particular attribute to 26. Then when we declare employee B and set it to A, we're simply taking B's memory reference and setting it to A. This is where shallow copies come from. So when we set B.age to 30, guess what? If we printed A.age to the screen, we'll see 30 because they refer to the same memory location. Let's contrast it again with the value type. Primitives, when you declare a primitive, they inherently hold the address. It's always a deep copy. When you, on the other hand, you're basically, when you do employee A and employee B here, you're basically giving yourself enough space for an address, like the address of an envelope. And when you write to it, you're writing an address, right? So that's how this works. Let's take a look at the null reference example. So null reference can be written this way. It's commonly, I tried to draw the way ground is written in electrical diagrams, and that used to be pretty common as a way of writing a null pointer. It's grounded, right? It refers to nothing. Employee A is equal to null, no memory. A.age is equal to 23. Null reference exception is thrown, right? So the program halts at that time, and hopefully there's a catch for it that will handle it. Otherwise, the program will be terminated. So Java always initializes the variables. It's automatic for object memory. It's automatic for object member variables. So if it's at level, let's say int I, and at the object member variable level, it'll be set to 0. But it's manual for local variables, meaning the compiler will make you set I is equal to 0. Right? This does not mean object handles refer to objects. They can refer to null. So I'm going to go back in history a little bit and to understand why Java is the way it is. Java was a fix for C in a lot of respects, to simplify it and to make it, and to answer sometimes the flaws that, the pitfalls of C that allowed programmers to make mistakes. So C does not throw on a setting of an initialized memory handle. So if this was C on the left-hand side in this example, employee A is equal to null, it would not throw when A.age is equal to 23. Well, what happens? If you have an uninitialized memory handle in C, that writes to an arbitrary location. What does an arbitrary location in memory mean? It's going to write over the top of another variable, some variable somewhere, or running code. Code is also stored in memory. Or it used to, before operating systems learned how to protect themselves, you could write in operating system space and just write over the top of it. This destabilized machines. It destabilized software. So software used to crash a lot more, and operating systems used to crash a lot more than they do now. Because we've learned how to do that, we should do null reference exceptions instead of allowing code to continue to run. So a more modern nevertheless, Java does allow null reference exceptions, and these are so common. I bet you, I worked at companies where no reference exception was by far our biggest maintenance task as programmers maintaining an application. I worked at a lot of companies. In fact, I think that's the majority area you see in production code is the no reference exception. So Kotlin comes around, and we had a discussion question on Kotlin. And to me, what caught my eye about that the main feature of language is that it discourages or prevents the setting of null to an object handle. So as Java was a fix for C, allowing, much worse, the setting of an uninitialized memory handle, the evolutionary step away from Java, Kotlin, which is not allowing null references to exist, or at least discouraging them. And I see that as a step forward. Okay. So next we're going to look at parameters and refer also where this distinction between value and reference types will come into play. Thank you.